The comparison between the 486 and Pentium processors revolves around the pipeline architecture, a critical factor that significantly influenced the performance and technological advancement of these two processors. The pipeline architecture revolutionized how processors handled instructions, dramatically increasing processing speed and efficiency. Let's delve deeper into how pipeline technology was designed and evolved in the 486 and Pentium processors, and uncover the secrets behind their advancements. Introduced by Intel in 1989, the 486 processor was a significant leap forward from its predecessor, the 386. It was based on a 32-bit CISC, complex instruction set computer, architecture, but what truly set it apart was the introduction of a 5-stage pipeline architecture. The 486 pipeline was structured into 5 distinct stages, much like an assembly line in a factory. First, instruction fetch. In this stage, the processor retrieves the instruction from memory. The program counter, PC, identifies the current instruction's location, which is then fetched via the system bus and brought into the processor. Second, instruction decode. The fetched instruction is decoded in this stage. The instruction decoder analyzes the opcode, operation code, to determine what operation needs to be performed. During this process, the necessary operands, data, are identified, and if needed, data is fetched from registers or memory. Third, execution. The decoded instruction is executed in this stage. The arithmetic logic unit, ALU, or floating point unit, FPU, performs the required arithmetic, logical, shift, or branch operations. Fourth, memory access. If the instruction involves memory access, this stage handles reading from or writing to memory. This is crucial for load, store instructions, where data is accessed from memory and stored in registers after processing. Fifth, write back. The final stage involves writing the results back to the processor's internal registers, making the data available for subsequent instructions. The 486's pipeline structure allowed these 5 stages to operate independently, enabling the processor to handle multiple instructions simultaneously. This architecture greatly improved instruction processing speed, as it allowed the processor to process more instructions per clock cycle compared to the previous serial processing methods. However, there was a significant challenge: branch prediction. When the program encountered a conditional branch, like an if-then-else statement, the pipeline had to predict which instruction to execute next. The 486's simple branch prediction mechanism often made incorrect predictions, leading to pipeline stalls. A pipeline stall occurs when the wrong instruction is loaded into the pipeline, requiring it to be cleared and refilled with the correct instruction. This process temporarily halts the pipeline, leading to a noticeable performance drop. While the 486's pipeline was innovative for its time, it had clear limitations, especially regarding branch prediction. Incorrect predictions could lead to frequent pipeline stalls, reducing the overall instruction throughput and impacting performance. To address these issues, Intel needed to develop more advanced pipeline technologies and branch prediction mechanisms in its next-generation processors, which brings us to the Pentium. Released in 1993, the Pentium processor was the successor to the 486, and it introduced Intel's superscalar architecture. The core idea behind this architecture was to maximize instruction-level parallelism, ILP, which significantly boosted performance. The Pentium processor's standout feature was its dual pipeline architecture. The processor had 2 independent pipelines, known as the U-pipe and the V-pipe, which could process 2 instructions simultaneously. U-pipe was a general-purpose pipeline capable of handling all types of instructions, especially the more complex ones. V-pipe optimized for simpler instructions. The V-pipe worked in parallel with the U-pipe to maximize instruction throughput. This dual pipeline structure allowed the Pentium to process 2 instructions per clock cycle, greatly increasing its processing power compared to the 486. The Pentium took branch prediction to the next level with advanced branch prediction. The Pentium's branch predictor used a 2-bit history-based predictor to analyze past branch behavior and make more accurate predictions. This significantly reduced the frequency of pipeline stalls caused by incorrect predictions. Additionally, the Pentium introduced speculative execution, an intriguing technique where the processor would pre-execute instructions along the predicted branch path. If the prediction was correct, the pipeline continued seamlessly, boosting overall performance. Even if the prediction was wrong, the impact on performance was minimized, as the pipeline didn't completely stall. Another major innovation in the Pentium processor was out-of-order execution. This technology allowed the processor to execute instructions out of their original program order if there were no data dependencies between them. For instance, if two instructions were independent of each other, the processor could execute them in parallel, making better use of the pipeline's resources. Moreover, the Pentium implemented dynamic execution, which dynamically reordered instructions to execute them in the most efficient sequence. This further enhanced instruction throughput and ensured that the pipeline operated as smoothly and efficiently as possible. Pentium Superpipeline Technology further refined the pipeline process by subdividing existing pipeline stages into smaller, more precise stages. For example, the instruction fetch stage could be broken down into multiple substages, allowing for overlapping fetch operations. This increased the pipeline's clock speed, enabling the processor to complete more instructions in a given time frame and improving overall system performance. The 486 processor's 5-stage pipeline significantly improved instruction processing speed, but its limitations, such as basic branch prediction and single pipeline structure, constrained its performance. The inability to handle multiple instructions simultaneously and frequent pipeline stalls due to incorrect branch predictions were major drawbacks. In contrast, the Pentium processor's dual pipeline architecture, coupled with advanced technologies like advanced branch prediction, speculative execution, out-of-order execution, dynamic execution, and superpipeline technology, allowed for a far more efficient and powerful pipeline. The Pentium could process multiple instructions per cycle, handle branch predictions more accurately, and keep the pipeline running smoothly even in complex scenarios. The pipeline architecture of the 486 processor was groundbreaking for its time, marking a significant advancement in Intel's microprocessor design. However, the Pentium processor took this foundation and built upon it, overcoming the 486's limitations and delivering a leap in performance that set the stage for modern CPU design. Pentium's innovations in pipeline architecture, particularly its ability to process instructions in parallel and handle complex branching scenarios, laid the groundwork for the multi-core, parallel processing capabilities we see in today's CPUs. The journey from the 486 to Pentium is a testament to how technological evolution drives continuous improvements in computing power, leading us to the highly efficient and powerful processors that power our devices today.
The first rule of channel is subscribe channel. Second rule of channel is click like. This channel will make you smart.